This presentation is called What is Emissivity? It's very important to understand that so that you can get a proper reading on the target you're measuring. Emissivity is the ratio of the true emitted energy from an object versus that reflected from a perfect emitter called a black body. The black body has an emissivity of 1, meaning that everything coming off of it belongs to it. The opposite is a perfect reflector, like a mirror. The emissivity of a mirror is 0. What that means is that you don't see anything coming from the mirror itself. You can't measure it. You're seeing whatever is reflected from its surroundings wherever it's installed. This is a formula called Kirchhoff's law. What it means is that the target you're measuring will have emitted energy, they will probably have some reflected energy, and they will have maybe some energy transmitted from something that's hot behind it. What you need to understand is what is important to me in this measurement. We always want the emitted energy. We want to get rid of the reflected energy. And you may want or may not want the transmitted energy, depending on what kind of a factor it is in the overall reading you want. So let's say the emissivity of this surface is 0.7. That means that red bar, the emitted energy, is 70% of the total energy coming off this. That reflected energy, the blue bar, could be 30%. We want to get rid of that. This is a typical portion of an emissivity chart. Common objects will tell you the emissivity of common products. There are a number of people who will have these, different manufacturers, and for instance, the oxidized copper, you may not have the same reading for every manufacturer, but they'll be close. What this is a beginning or a starting point for you then to fine-tune with your instrument itself to get the final result based on what you're measuring. There are charts available. This one was an 8 to 14 micron, which is long wavelength. They're the most common. There are short wavelength charts available, which we can supply. As the temperature of a target increases, the emissivity will start to change. So for instance, an 8 to 14 micron unit, which measures anything within the ambient temperature you live in or ambient area you live in. If you get above a point of, say, 1200 degrees, the emissivity of your target begins to change pretty rapidly, so you're not going to get a good reading with that spectral range at those high temperatures. This is a picture of an iron. It's painted with a flat black paint on the left side, and the right side is left as it came from the factory. The temperature on the iron in this particular picture is 248 degrees all the way across. And yet the temperature we took with an infrared thermometer showed 284 on the left side, but about 99 on the right side, because what it's doing is reflecting the cool environment all around it. See this 0.98. Tell me when you've got that.
I'm rolling.
So we're doing this black inside, which is acting like a black body, and what it puts off belongs to it. Now I'm going to go over to the shiny side, same emissivity setting, and you can see how the change in temperature shows the difference in emissivity. This is a chart called Planck's chart. As you see, as the temperature goes up, the wavelengths get shorter and shorter, as shown below at the bottom of the chart. The very highest temperature across the top of this is the temperature, the surface of the sun. And you see that, like for instance, the next lower one, you're going back into the visible, you're heating metal up, so you'll start to turn red and then yellow and white if you keep heating it. So that moves that back into the visible part of the spectrum. The temperature of the sun, you go through the visible light back into the ultraviolet, and again, the energy on both sides of that visible part from the sun is invisible. A good example of that that you may see how it works is the short wavelength sunlight will come through the windows of a building. long wavelength energy won't. But when it hits the inside surfaces, it bounces back, and that changes at the long wavelength. Now that energy can't get it back out through the glass. That's why a greenhouse will get hot in the sun even on a cold day. This is a overview of the spectral ranges: long wavelength, mid wavelength, short wavelength, and then at the very bottom of the chart is near infrared. That's a spectrum, but it's actually below 1, and it's for very high temperature specialized measurement. If the emissivity of an object is unknown, you can work it out a couple of different ways. If you have a good contact probe and it's not a live electrical circuit, which you don't want to touch, or something is moving, it might be dangerous, you can put a contact probe on it, get a reading, and adjust the emissivity on your infrared thermometer. You get the same reading. Now you're calibrated to that surface. Another way to do it is determine getting the emissivity of the surface is you want to heat your surface to at least 20 degrees above or even below, or cool it to below, so that any reflected issues from surrounding things at the same ambient temperature will not affect it. So you can use masking tape, electrical tape, a flat finish paint, or titanium dioxide powder, which we know the emissivity of, and you can put that on a surface. Like, for instance, you saw a little while ago that plastic on that stainless calendar roll. If you wanted to measure that temperature of that calendar roll being shiny, you can't do it with an infrared thermometer. So you can put a little band of flat black paint along the edge of it and measure that. So that way you can adjust your infrared thermometer to the same emissivity of the tape or the paint, get a reading, and then go off to the side and get the same reading by adjusting it to the surface of that material. Any questions on emissivity? It's very important if you're going to get a true reading on your target. You have to know what's reflected to get rid of that. You don't want that to affect your readings.